Hello everyone, today we'll go deeper into the world of deployment and automation for microservices, focusing on CI/CD processes. So let's ask ourselves a simple question. When is our code is really ready for production? Because locally everything looks nice. We run it, it works, test, pass. Production is a very different story. Well, we must answer at least these questions. How can we make sure that new chains will not break other services? Everything is connected and even a small bug can cause a chain reaction. How can we build a stable production environment when we have dozens of microservices? Here we cannot rely on luck. We need clear organization, monitoring, and control. How can we release new code often, but in such a way that users don't even notice? For us, it's just another deploy, but for the user, the service must always work without interruptions. Answers to these questions show if our code is really production ready, not just existing, but living and surviving in real conditions. Well, continuing our talk about production readiness, we cannot skip such an important concept as the 12-factor app. Actually, it is a software development method published by Heroku in 2017. It gives clear rules for building modern cloud applications. So let's go through each factors and see what they mean. One codebase, many deploys. This principle means you do not create separate repositories for stage, production, or dev. You have only one source code and you deploy it to all environments. Dependencies declared clearly. All dependencies and extra packages must be written down clearly. For example, in JavaScript, you use package.json. This makes the environment predictable and easy to reproduce. Config stored in the environment. Configurations like database access or API key should live outside the code, so you keep them in environment variables. This way you can change configs without changing the code. Backing services as attached resources. Services like PostgreSQL, MongoDB, Kafka, Redis, or payment systems are treated as external resources. Your app just gets connection detail from the environment. This gives flexibility to replace one service with another without code chains. Build, release, run. The build step, for example, a Docker image, is separate from running it. This avoids problems when a hotfix is delayed because you rebuild everything. Each environment should use the same artifact. Stateless processes. Your app should run as stateless processes. Any state like user session must be saved in a database or cache, so you can start many instances without sync issues. Port binding. Every service should expose itself through a network port. This allows multiple processes on the same server and easy communication. Scale out with processes. Scaling means adding more processes or containers. This horizontal scaling is more flexible than just making one server bigger. Fast start and graceful shutdown. The app should start fast and shut down nicely, so it finishes current requests without losing data and then stops. This improves availability. Dev and prod parity. Development, test, and production environments should be as similar as possible. In fact, this helps find bugs early and make sure that what works on stage also works on production. Logs as event streams. Logs should be seen as event streams, not as saved files. A central logging system collects and processes them. And admin tasks as one-off processes. Tasks like database migrations or a script should run as separate processes, not inside the main web server. So this keeps operations apart from business logic. So the first thing that happens after we write code is the build stage. Here we need to create something we can already run. For example, it can be a Docker image for the backend or a JS bundle for the frontend. This stage is closely connected with the 12-factor app we saw before. The fifth factor says build, release, run. This means building an artifact and running it are two different processes. CI pipelines help us do this by creating immutable artifacts. These artifacts can be deployed to any environment. It also supports the second factor, dependencies declared clearly, because CI checks that all dependencies are defined correctly. And it supports the 10th factor, dev and prod parity, because we test the same artifact in different environments. So, now let's talk more about continuous integration, or CI. CI is a concept with one main goal, synchronization of all parts of the system. This is done through frequent checks of code chains to see if they can work together with other code or services. CI is a continuous process of integration checks. Why do we need this? Thanks to CI, we can check our code often in small pieces, so we avoid problems with huge packs of chains that take weeks to test, fix, and merge. These big packs often create what we call bloody marys. And finally, CI also checks if the code builds at all. For example, it runs linters, security, and typing checks. After our code passes the continuous integration stage, where we check its sync and quality, we move to the next phase, continuous delivery and continuous deployment. This is a continuation of the CI/CD pipeline, which automates delivering chains to the environment. Well, there are two main approaches, often called CD, but with one key difference. First, continuous delivery. It makes sure your code is always ready to go to production. The pipeline is automated from build and test to deployment. But continuous delivery needs a manual step before production. This manual approval is like a safety check, but it usually creates delays. On the other hand, we have continuous deployment. This is a fully automated process with no manual steps. You open a pull request or merge request, and the pipeline starts automatically. It runs linters, tests, building a Docker image, and checks everything. If all checks pass, the code is deployed to production right away. This lets engineers focus on development and deliver changes fast. It works best for frequent and small updates. So the main difference between continuous delivery and continuous deployment is the presence or absence of a manual step before production. In practice, CI is organized with CI/CD pipelines. A typical pipeline may include these steps. Linter analyzes hot style, formatting, and basic errors. Vulnerability scan checks dependencies and containers for known security issues. Schema generation creates or updates API or database schemas, for example, OpenAPI, GraphQL, or migrations. Compilation build the source code into artifacts like binaries, jars, or vars. Testing runs unit integration or end-to-end tests to check functionality. It is important to build the pipeline so that the fastest tests, like unit tests, run first. This gives quick feedback and helps find small mistakes early without waiting hours for full integration tests. After unit tests, we run service tests and then maybe contract tests. Contract tests check service interaction without deploying them. Docker image creation packages the app and its dependencies into a container. Deployment to multiple environments. Deliver the app to dev, staging, and production for validation and use. So, these are many tools that help automate all steps from building code to deploying it. Here are some of the most popular ones. Jenkins, one of the oldest and most flexible tools. It allows you to set up almost any pipeline thanks to a huge plugin ecosystem. Travis CI. This tool was one of the first in CI/CD automation, though today it may not be as popular as before. GitLab CI/CD. Integrated into the GitLab platform, very convenient for teams already using GitLab for repositories. Pipelines here are configured with YAML files. GitHub Action, a solution from GitHub that lets you set up pipelines directly in your repository. It can use webhooks to interact with other tools, for example, Jenkins. And TeamCity, another tool that also gives wide possibilities for CI/CD. So, now we move to the deployment stage. Here we should follow some principles. Isolation. This means keeping microservices separate from each other. It is important to avoid the noisy neighbor problem, when one service uses too many resources and hurts the performance of others. Automation. Since microservice architecture may include 20, 30, or even thousands of services, maximum automation is critical. Doing all deployment manually would be almost impossible. State management. This is about the ability to control the cluster and service interactions. For example, turning interaction on or off, running migrations, and controlling your environment. Now, let's look at the available deployment options: physical servers, virtual servers, containers, platform as a service, and function as a service. And now we'll review each of them in more detail. Let's start with physical servers. Their main advantage is a high level of isolation. Your service can run on a separate physical computer without any neighbors. However, their resource utilization is usually poor. We often buy physical servers with a big reserve, but in the beginning, our processes do not use all those resources. Also, they have low flexibility. It is hard to scale, to manage resources automatically, or to start new instances quickly. They almost have no automated state management, which makes them a bad choice for microservices. They are mostly used for monoliths, legacy system, or special cases where hardware optimization is needed. For example, high performance computing. Now let's look at virtual servers. The level of isolation here becomes worse compared to physical servers. The hardware is shared, and this can cause the noisy neighbor problem, as well as network traffic being eaten by other services in the cloud infrastructure. However, the resource utilization is already better. You can easily and quickly change the type of instance or even automate this process, finding the best balance between price and resources. Because virtual servers are usually available through cloud solutions, they provide a huge amount of automation and tools. This makes it possible to automate releases, to reach their downtime, and to effectively control the state of the cluster. But virtualization has its price. This extra layer affects performance, although in practice it is rarely critical for average web development. There is also redundancy. Imagine that you have 10 microservices, and each one uses 20 megabytes. But on each virtual server, you must install an operating system, binaries, and utilities, which take a large amount of disk space. Automated scaling is possible here, but it requires some time for setup and configuration. In general, virtual servers are a possible solution for microservices, especially because of the wide set of tools that cloud providers give. They allow you to work with them almost as flexibly as with containers, although at a little higher price. To compare them with physical servers, we can use this analogy. A physical server is like your own house, full independence but expensive and not flexible. A virtual server is like an apartment in a big building. You have your own space, but you share resources with neighbors. Continuing our talk about choosing infrastructure after physical and virtual servers, it is logical to move to containers, which today are one of the most popular solutions for deploying microservices. Containers are a good solution for microservices. Their architecture is perfect for microservices where each service runs in an isolated but easy to manage environment. Let's look at their advantages in detail. First, they give good resource utilization, allowing you to run several containers on one server. This is different from virtual machines, where each machine needs its own operating system, creating redundancy and worse utilization. With containers, the operating system is reused, which reduces the virtualization cost and redundancy. There are many patterns for zero-downtime deployment and flexible state management. Containers also provide a high level of automation. Scaling containers is usually fast. This lets the system adapt quickly to load changes by automatically increasing or decreasing the number of microservice instances. In addition, cloud solutions give many tools for working with containers. These include services like Amazon Elastic Container Service and Google Kubernetes Engine, as well as open source solutions like Kubernetes and Docker Swarm. These orchestration tools make managing a large number of containers much easier. However, containers also have disadvantages. They provide weaker isolation than virtual machines. This can lead to the noisy neighbor problem. Since containers have no hardware level limits, if one container suddenly uses all the memory, your container can also crash unless you configure limits. Despite this drawback, containers remain a very effective solution for microservices architecture, giving a balance between isolation, flexibility, and efficiency, especially when combined with powerful orchestration tools. After we talk about containers as an effective solution for microservices, the next question is how to manage them. When the number of containers grows, we need container orchestration, tools that manage many containers at once. Orchestration automates deployment, scaling, networking, and makes the system fault tolerant. And today, the market standard here is Kubernetes. Of course, it is impossible to explain Kubernetes in just a couple of slides. People create whole lectures and conferences about it. So I just want to give you a high-level overview and share a few important points. In Kubernetes, there are two main parts, the master node and the worker nodes. On the master node, we have services that control the whole cluster. API server. It receives all requests and commands from users or other services. Controller manager. It makes sure that the desired state matches the real one. For example, if we say there should be 3 pods, it checks and restores them if they fail. Scheduler. It decides on which worker node a new pod should run. etcd. This is a database that stores all cluster state information. On the worker node, we have the component that runs the applications. Kubelet. It gets tasks from the master node and runs pods. Kubeproxy. It takes care of networking, routing, and access to pods. Endpods. This is the smallest unit in Kubernetes that contains one or more containers. And now let's talk a little about the flow, for example, when we want to deploy one of our microservices. Everything starts with YAML files. First, we describe the desired state of the system, which microservices should run in the deployment YAML, how they should be available in the service YAML, and how to manage external access in the ingress YAML. For example, in a YAML file, we can say which Docker image to use, how many pod replicas to start, and what resources to give them. So first we run kubectl, apply and pass the YAML files. For example, deployment YAML or service YAML. Then the API server receives our instructions, checks them, and saves the desired state in etcd. This is like a fixed promise of the system. The pods do not exist yet, but there is already a record that they must appear. Next is the controller manager. The controllers look at this new state and start the creation process. For a deployment, it means create a replica set and the needed pods. At this moment, the pods exist, but they are in pending status, not yet placed on nodes. Then the scheduler takes the pods in pending status and decided where to run them. It checks the resources of each worker node, looks at limits and policies, and then assigns a node. After that, the kubelet on the chosen node gets the task and starts the pod as described in the deployment. Then the container runtime, Docker. It starts the containers inside the pod and makes sure they stay in the right state. Finally comes the network. Kubeproxy creates routing rules, set IP addresses, and configure load balancing. Thanks to the service YAML, other pods or even external clients can reach our application. In the end, we have running application available inside the cluster and, if needed, from outside too. Continue our review of deployment options for microservices. Let's move to platform as a service. This approach is a simple solution with limited customization and it looks attractive for many teams. It is perfect for microservices, especially in cases where there is no DevOps team and infrastructure requirements are not very complex. In fact, it is a platform that takes care of most infrastructure tasks, so development can focus only on writing code. Let's see how it works and what benefit it has. Platform as a service solutions often provide a user-friendly interface where you can upload your code or a Docker container, fill in the needed configuration, and the platform will run your service, giving you an access point to it. It requires minimal DevOps resources, since even a developer without deep infrastructure knowledge can use it. The entry level is very low, almost like setting up a local service. It works well when your project does not need very complex infrastructure requirements, when you don't need deep customization, or when you will not face critical performance issues. And the cost of solving such issues is not very high. Some examples of a platform as a service solutions are Heroku, which is very popular in this area, Google App Engine from Google, and Cloud Foundry. Each cloud provider usually had its own solution with similar functions. However, it is important to remember about the limitations. If your project has DevOps specialists, or if you are ready to invest time in learning more flexible solutions such as Kubernetes, then you should consider them. While platform as a service gives simplicity and fast start, Kubernetes is a better choice for long-term company growth when scaling and high flexibility are needed. So this is a trade-off between easy of use and flexibility with full control over infrastructure. And now we move to function as a service, better known as the serverless approach. This is a very flexible solution that runs a service on a specific trigger. For example, an HTTP request, a message in a queue, a new file in storage, or a scheduler cron job. After execution, it immediately shuts down. Imagine it as a container that starts for every single request and then stops right after it finishes. If 1,000 requests arrive at the same time and the configuration allows it, the platform will start 1,000 containers, they will process the requests and then disappear. This gives explosive scaling, where you can go from 1 to 1,000 instances very fast. It is a serious advantage for systems with variable or unpredictable load. However, this approach has its own downsides. One of them is the function startup time, or cold start, which may take from 1 to 3 seconds. This is not always acceptable for APIs that need responses in the milliseconds range. Although there are techniques for warming up functions, where a container does not fully shut down but stays ready for quick restarts. This makes execution much faster. About pricing, function as a service solutions have a specific model based on the number of parallel runs, the amount of allocated resources like memory or CPU, and the execution time. This can be cost-effective for rare or short tasks, but not always predictable for long-running or always active services. Examples of function as a service solutions include AWS Lambda, Azure Functions, and Google Cloud Functions. For easier deployment of function as a service solution, especially AWS Lambda, the serverless framework is widely used. This tool allows you to describe infrastructure and configuration in YAML files. Looking at this YAML, the framework automatically creates all needed cloud resources, register functions, and connect them to the API gateway. This makes managing a serverless architecture much easier. Function as a service is not a solution for every service. It is good for very specific event-driven tasks, for example, file processing in storage or scheduler job. But if your API must run constantly and needs stable, predictable performance with low latency, then deploying it as a regular container is a better choice. And now let's look in more detail at this concept, which I believe it must have for microservices. Infrastructure as a code is a practice of managing and providing infrastructure such as network, virtual machines, load balancers, and databases through configuration files instead of manual setup. This means that all your infrastructure is described in files stored in a version control system, for example Git, just like your application code. Let's go through the main benefits of IOC. Reducing vendor lock-in. Of course, a full migration from one cloud provider to another will still require rewriting configuration files. But IOC allows you to make this process much easier. You are not tied to manual console settings. You have code that you can adapt. A valuable part of disaster recovery plan. As we already discussed, if you lose a whole environment, for example, because of a data center failure, it lets you quickly restore infrastructure just by running a few commands. Automation of similar solutions. DevOps teams can describe infrastructure once and then easily create different environments, dev, stage, prod, or even new projects using the same code. This gives reproducible environments. Environment consistency. It helps keep all environment as similar as possible. This reduces the number of bugs that may appear when moving from one environment to another, making work easier for DevOps and developers. Instead of waiting for DevOps engineers to manually create a resource, for example, an S3 bucket, a developer can just create a pull request with changes in the IOC configuration. After review and merge, the resource will be created automatically. This unblocks teams and speed up development. One of the most popular tools for IOC is Terraform. It allows you to describe infrastructure for different cloud providers, such as AWS, Google Cloud, Azure, and many others, using one configuration file syntax. Terraform lets you declare the desired state of your infrastructure, and then it automatically creates or modifies resources according to this description. For example, you can describe creating a Google Cloud VPC or AWS EC2 instances as shown on the slide. To sum up, infrastructure as a code is not just a good practice, it is a necessity for any modern microservice architecture, ensuring automation, reliability, and efficient infrastructure management. And now we move to a very important topic. How can we deploy our applications seamlessly so that users notice nothing? When we talk about seamless deployment, also called zero downtime, we mean a key strategy that let us update software without any downtime or service interruption. This gives users continuous access to the system even while we deploy new versions or fixes. The main goal is to avoid situations where old processes stop while new ones are only starting, which could cause service unavailability and hurt the user experience. I want to highlight two main and most popular approaches to achieve zero downtime deployment: blue-green deployment and Canary release. And now let's take a closer look at them. So let's move to blue-green deployment. The idea here is to use two identical environments which are called blue and green. In the blue environment, the current stable version of the application is running and serving all users. The new version of the software with all changes and updates is deployed in the other, the green environment. The deployment process looks like this. When the new version is successfully deployed in the green environment, the router or load balancer instantly switches all users' traffic from blue to green. This way, users starting using the new version without any visible interruptions or downtime. The old blue environment is not shut down immediately. It stays active to make a graceful shutdown, which means finishing all current requests that come before the switch. After that, the blue environment can be kept as a hot backup for a quick rollback in case problems are found in the new version. It is also important to keep in mind some aspects. For example, you need to ensure backward compatibility of the database schema. Also, these environments can exist permanently or they can be created only when needed. The implementation of this approach becomes much easier with cloud solutions and container orchestrator such as Kubernetes. Canary deployment is a strategy that allows you to gradually roll out changes to a limited group of users. Instead of instantly switch all traffic like in blue-green, the new version of the application runs in parallel with the old one. Only a small percentage of traffic, for example 10%, is redirected to it. This percentage can vary depending on risks and system sensitivity. The idea of this approach comes from the legend of canaries in coal mines. Miners used to take canaries with them underground to detect poisonous gases. If the bird dies, it was a danger signal and miners quickly left the mine. We do the same with our small percentage of traffic. If something goes wrong, it is an early warning signal. Okay, how does it work? While these small groups of users interact with the new version, monitoring carefully tracks errors, performance metrics, and other indicators. If potential problems appear, for example, many 500 errors, the system can automatically roll back to the old stable version, minimizing risk for the main audience. This makes it easy to revert changes, fix the issues, and then deploy the correct version again. If the new version works well and all indicators are normal, the traffic percentage is increased step by step, for example, to 25%, then 50, 75, and finally 100%. Canary deployment ensures a controlled and safe process of releasing changes, giving teams confidence in system stability and helping to avoid early mistakes or unexpected issues in production. Okay, today we focus on what it means to be production ready. Code should be released often without pain for the user into a stable, controlled environment with clear risk management. Next, we describe the 12-factor app, one repository for all environments, configs in environment variables, services are stateless and built-in separate from run. This is the base without its scaling and automation do not work well. CI keep the code in order, build, linters, security checks, tests, all in small pieces, all the time. CD continues the story with manual configuration before production, continuous delivery, or without any manual steps, continuous deployment. We looked at typical CI/CD pipeline. Then we explore the option for deployment: physical servers, virtual servers, containers, platform as a service, or function as a service. The choice depends on isolation, cost, and speed. For managing containers at scale, we use Kubernetes. We describe the desired state in YAML files, and it brings reality to that state. To keep everything reproducible, we use infrastructure as code. Terraform describes infrastructure in code, removes manual routine, and gives identical environments. And finally, we release with zero downtime. For that, we use blue-green with instant traffic switch or Canary, where the new version gets a small part of the audience. And we watch metrics and roll back if needed. Here is a short test to see how much you understand. And I really appreciate your attention today. Thank you all. Bye bye.